250 million years ago, beneath skies thick with volcanic aerosols and carbon dioxide concentrations exceeding 3,000 parts per million, a single landmass dominated the surface of Earth, stretching from pole to pole across more than 100 million square kilometers of the planet's crust. A continental assembly so vast that its interior regions lay 1,500 kilometers from the nearest ocean, creating climatic extremes unknown in any subsequent geological epoch. This supercontinent, assembled through the patient collision of ancient cratons and island arcs over tens of millions of years, represented the culmination of plate tectonic forces that had gathered the scattered fragments of Earth's lithosphere into a configuration that would fundamentally alter the trajectory of life itself, concentrating terrestrial ecosystems into a unified arena where evolution, climate, and catastrophe would intersect with unprecedented intensity. The shorelines of this immense landmass traced irregular patterns around a single vast ocean called Panthalassa, while within its embrace a smaller sea, the Tethys, carved an embayment into the eastern margin, creating maritime corridors that would influence atmospheric circulation and oceanic chemistry across the entire globe. The formation of this continental giant had required the closure of ancient oceans, the destruction of seafloor crust older than any that survives today, and the elevation of mountain ranges whose eroded remnants now lie buried beneath younger sediments, or scattered across multiple modern continents, their original continuity evident only through careful geological reconstruction and the matching of rock types, fossil assemblages, and structural trends across thousands of kilometers of present oceanic separation. The assembly of Pangea began in earnest during the late Paleozoic, as the southern supercontinent of Gondwana, already an ancient amalgamation comprising what would become South America, Africa, India, Australia, and Antarctica, moved northward through the slow but inexorable process of seafloor spreading and subduction, eventually colliding with Laurussia, the merged entity of North America and Europe that had itself formed through earlier tectonic unions. This collision occurred along a suture zone that would generate the Appalachian Mountains in eastern North America and their counterparts in northwestern Africa and western Europe, mountain ranges that at their peak may have rivaled the modern Himalayas in elevation, their roots extending deep into the lithosphere where metamorphic processes transformed the colliding crustal materials under pressures exceeding 10 kilobars and temperatures approaching 800 degrees Celsius. The final piece of the assembly involved the accretion of several smaller continental blocks and volcanic arcs along the eastern margin of Pangea, creating a complex mosaic of terrains that reflected the diversity of Earth's plate tectonic processes, while the western coast of the supercontinent remained relatively passive, facing the vast Panthalassa Ocean where subduction zones consumed oceanic lithosphere along distant margins. The geometry of this continental configuration created a massive shadow in Earth's hydrological cycle, as moist air masses from the surrounding ocean struggled to penetrate the interior regions, resulting in the development of enormous desert systems that stretched across the heart of the supercontinent, their extent dwarfing any desert environment present on Earth today, with annual precipitation in some areas potentially falling below 50 millimeters and seasonal temperature variations exceeding 60 degrees Celsius between summer and winter in the continental heartland. Within the stratigraphic record of Pangea's existence lies evidence of profound environmental transformations that would challenge the persistence of life across multiple domains, most notably during the transition between the Permian and Triassic periods, approximately 252 million years ago, when Earth experienced the most severe mass extinction event in the history of complex multicellular organisms, an episode of biotic crisis that eliminated more than 90% of marine species and 70% of terrestrial vertebrate families within an interval that geological evidence suggests may have lasted fewer than 60,000 years. The causes of this extinction, while still debated in their relative contributions and precise mechanisms, appear to have originated in the massive volcanic eruptions of the Siberian Traps, a large igneous province that released approximately 4 million cubic kilometers of basaltic lava across an area exceeding 7 million square kilometers in what is now northern Russia. Eruptions that also injected enormous quantities of carbon dioxide, sulfur dioxide, and halogen compounds into the atmosphere, initiating a cascade of environmental changes that would propagate through Earth's interconnected systems. The initial phase of eruption likely produced sulfate aerosols that temporarily cooled global temperatures through the reflection of incoming solar radiation, but this cooling would have been brief, lasting perhaps only a few years before the longer-lived greenhouse gases accumulated to concentrations sufficient to drive temperatures upward by 6 to 8 degrees Celsius in equatorial regions and potentially 10 to 14 degrees in polar latitudes. The warming itself would have stressed ecosystems already adapted to the climatic extremes of Pangea's continental interior, but the secondary effects proved even more lethal, as increased weathering rates, changes in oceanic circulation patterns, and the release of methane from seafloor deposits combined to create conditions in which oxygen concentrations in both marine and terrestrial environments declined to levels that challenge the metabolic requirements of complex organisms. The ocean surrounding and penetrating Pangea underwent transformations that left signatures in the chemical composition of sedimentary rocks deposited during the extinction interval, signatures that revealed declining oxygen levels, enhanced weathering inputs, and changes in the carbon cycle that suggest fundamental disruptions to the biological pump that normally transfers organic matter from surface waters to the deep sea. In many basins, the boundary between Permian and Triassic strata is marked by a thin layer enriched in clay minerals and depleted in calcium carbonate, reflecting a period when carbonate-producing organisms had largely disappeared, and when the chemistry of seawater shifted toward more acidic conditions, a consequence of elevated atmospheric carbon dioxide dissolving into surface waters and reducing carbonate saturation states below the thresholds necessary for shell formation. Beneath this boundary layer, Permian rocks often contain diverse assemblages of brachiopods, bryozoans, crinoids, and other marine invertebrates that had dominated Paleozoic seas for hundreds of millions of years, their body plans and ecological strategies refined through countless generations of evolutionary innovation. While above the boundary, Triassic rocks initially preserve only sparse fossil assemblages dominated by a few stress-tolerant species, creating a pattern that paleontologists describe as a disaster fauna, communities of organisms capable of surviving in degraded environments, but lacking the diversity and complexity that characterize healthy marine ecosystems. The recovery from this extinction would require millions of years, during which time the vacant ecological niches slowly filled with new lineages whose ancestors had survived the crisis through combinations of physiological tolerance, favourable geographic positioning, or simple chance. On the terrestrial portions of Pangea, the extinction manifested differently, but with comparable severity, as vertebrate communities that had diversified throughout the Permian, including large herbivorous synapsids such as the paraeosaurs and dicynodonts, apex predators like the gorgonopsids, and a variety of smaller insectivorous and omnivorous forms, suffered dramatic population declines that in many cases led to complete lineage extinction. The fossil record from terrestrial sequences in South Africa, Antarctica, Russia, and other former components of Pangea documents this transition through changes in faunal composition, body size distributions, and ichno-fossil diversity, showing that the complex, multi-tiered terrestrial ecosystems of the late Permian collapsed into simpler communities dominated by a small number of surviving taxa, particularly certain lineages of dicynodonts that appear to have possessed physiological adaptations enabling survival under conditions of reduced oxygen availability and elevated environmental stress. The extinction on land correlates with evidence of enhanced wildfire activity, as preserved charcoal layers indicate that even as ecosystems deteriorated, periodic burning continued to shape landscapes, possibly exacerbated by increased lightning frequency under altered atmospheric conditions or by the enhanced flammability of vegetation stressed by climatic extremes. The soil profiles from latest Permian and earliest Triassic sediments show signs of reduced biological activity, with simpler root structures, less developed soil horizons, and geochemical signatures suggesting decreased carbon storage in terrestrial reservoirs, all pointing to ecosystems operating at diminished capacity during the crisis interval and its immediate aftermath. The persistence of Pangea as a unified landmass through the early and middle Triassic period, spanning approximately 30 million years following the end Permian extinction, provided a geographic stage upon which the survivors of the crisis could radiate into the ecological spaces left vacant by the extinction, leading to the emergence of entirely new community structures and evolutionary innovations that would define the Mesozoic era. Among the most significant of these innovations was the rise of the archosaurs, a lineage that would eventually give rise to both dinosaurs and crocodilians, groups that began their diversification in the shadow of the Permian-Triassic boundary, but which by the Middle Triassic had begun to establish the ecological dominance that would characterize the remainder of the Mesozoic. The Archosaur success appears to have been facilitated in part by respiratory innovations, particularly the development of air sac systems and flow-through lung ventilation that increased oxygen extraction efficiency, adaptations that would have provided significant advantages under the reduced oxygen concentrations that persisted for millions of years after the extinction event, concentrations that modelling studies suggest may have remained below 17% in some regions, compared to the 21% that characterises modern sea-level atmosphere. Alongside the Archosaurs, other lineages also diversified, including the cynodonts, advanced synapsids that would eventually give rise to mammals, and various reptilian groups that explored ecological niches ranging from marine habitats to arboreal environments, demonstrating the creative potential of evolution even in the aftermath of catastrophic biodiversity loss. The climate of Triassic Pangea remained hostile by modern standards, with continued evidence of extreme seasonality, limited polar ice accumulation, despite high latitude temperatures occasionally dipping below freezing, and persistent aridity across much of the continental interior, conditions that shaped the distribution of plant communities and influenced the biogeographic patterns of animals that depended upon them. The vegetation of this period underwent its own revolutionary changes, as the seed ferns and other Paleozoic plant groups that had survived the extinction found themselves competing with newly diversifying conifers and other gymnosperms that possessed adaptations for efficient water use and reproduction in arid environments, including reduced leaf surface areas, thick cuticles resistant to water loss, and seeds protected by substantial integuments that could withstand desiccation during dormancy. These botanical changes had cascading effects through terrestrial food webs as herbivores adapted to new plant chemistries and physical structures, while predators tracked the shifting distributions of their prey across landscapes, where rainfall patterns, soil development, and topographic relief created complex mosaics of habitat types, from the vegetated lowlands along ancient river systems to the sparsely populated uplands of the continental interior, where only the most stress-tolerant organisms could persist. The fossil record from Triassic rocks preserves evidence of these communities in exceptional detail at certain localities, particularly in deposits where rapid burial or unusual preservational conditions captured not just skeletal remains, but also soft tissues, trackways, coprolites, and other traces of ancient life, enabling paleontologists to reconstruct ecological relationships and behavioral patterns with a precision rare in deep-time studies. As the Triassic period progressed into the Jurassic, approximately 200 million years ago, Pangea began the long process of fragmentation that would eventually lead to the modern configuration of continents, initiated by the development of rift zones along lines of crustal weakness that reflected ancient suture zones or regions of thermally induced lithospheric thinning. The earliest stages of this breakup involved the separation of North America from Africa along what would become the Central Atlantic Ocean, a process marked by extensive volcanism as basaltic magma intruded through the extending crust, creating dike swarms and sill complexes that now crop out from eastern North America through Morocco and into Brazil, forming a large igneous province known as the Central Atlantic Magmatic Province, whose eruption coincided with yet another mass extinction at the Triassic-Jurassic boundary. This extinction, while less severe than the end Permian event, nonetheless eliminated approximately 75% of species and opened ecological opportunities that would be filled by the rapid diversification of dinosaurs, who transitioned from relatively minor components of Triassic ecosystems to dominant large-bodied terrestrial vertebrates throughout the Jurassic and Cretaceous. The volcanism associated with continental rifting injected additional carbon dioxide into the atmosphere, maintaining elevated greenhouse gas concentrations and warm global temperatures that prevented the accumulation of substantial polar ice, even as the continents began their slow drift toward more dispersed configurations, a thermal state that would persist for much of the Mesozoic, and which profoundly influenced patterns of oceanic circulation, nutrient distribution, and marine productivity across the expanding ocean basins. The progressive separation of Pangea's constituent blocks proceeded through multiple stages, each involving the formation of new oceanic crust along spreading ridges and the accompanying adjustments in global plate motions as the forces driving plate tectonics redistributed themselves across Earth's surface. The South Atlantic Ocean began opening approximately 130 million years ago as South America separated from Africa, while the Indian subcontinent rifted away from Antarctica and began its northward journey that would eventually culminate in collision with Asia and the formation of the Himalayan mountain range. Australia remained attached to Antarctica longer, not separating until approximately 80 million years ago, while the final configuration of the North Atlantic involved multiple phases of extension, and the eventual separation of Greenland from Europe during the Paleogene, approximately 55 million years ago. Each of these rifting events generated distinctive geological features, including passive continental margins characterized by thick sedimentary sequences deposited as the newly formed ocean basins subsided and accumulated terrigenous and pelagic sediments, volcanic passive margins where mantle plumes contributed to the breakup process by thermally weakening the lithosphere and providing additional sources of magma, and transform margins where continental separation occurred along strike-slip faults, rather than purely extensional boundaries. The remnants of Pangea's assembly are still visible in the geological structures that span multiple modern continents, including the Appalachian Caledonian Mauritanian mountain belt, the matching coastlines and geological provinces of South America and Africa, and the distribution of Permian and Triassic fossil assemblages that occur in regions now separated by thousands of kilometers of ocean. The breakup of Pangea fundamentally altered Earth's climate system by changing patterns of oceanic and atmospheric circulation, increasing the length of coastlines and thereby moderating continental temperatures through enhanced maritime influence and creating new oceanic gateways that allowed the development of circumpolar currents, particularly around Antarctica, once it became isolated in its polar position during the Cenozoic. These changes contributed to the long-term cooling trend that began in the late Cretaceous and continued through the Cenozoic, eventually leading to the development of permanent ice sheets on Antarctica approximately 34 million years ago, and the onset of Northern Hemisphere glaciation approximately 2 to 3 million years ago, transforming Earth from the greenhouse state that had characterized much of the Mesozoic to the icehouse conditions that have prevailed during the Quaternary period. The dispersal of continents also influenced the evolution and biogeography of terrestrial organisms by creating barriers to dispersal and gene flow, leading to the independent evolution of distinct faunal assemblages on different land masses, a process particularly evident in the mammalian radiations that occurred following the Cretaceous-Paleogene extinction 66 million years ago, when the non-avian dinosaurs disappeared and mammals diversified to fill ecological roles ranging from small insectivores to large-bodied herbivores and apex predators. The modern distribution of plant and animal lineages reflects both the Pangean heritage of widespread distributions during the Permian and Triassic, and the subsequent vicariance and dispersal events that occurred as the supercontinent fragmented, creating biogeographic patterns that can be decoded through phylogenetic analyses that reveal the timing and sequence of lineage divergences. The legacy of Pangea extends beyond its influence on biological evolution and climate, to encompass the fundamental processes that govern Earth's long-term geological evolution, demonstrating that plate tectonics operates not merely as a mechanism for shuffling continents, but as a system that integrates mantle convection, crustal recycling, atmospheric chemistry, and biological innovation into a dynamic planetary process operating across scales from individual mineral grains to global patterns persisting for hundreds of millions of years. The supercontinent cycle, of which Pangea represents the most recent complete assembly, appears to be a recurring feature of Earth's history, with evidence suggesting that earlier supercontinents formed and dispersed during the Proterozoic and Archean eons, each assembly and dispersal potentially influencing atmospheric composition, oceanic chemistry, and the conditions available for life through mechanisms that remain subjects of active investigation. The stratigraphic record preserved in rocks that once formed parts of Pangea continues to yield insights into these ancient processes, as new analytical techniques enable geologists to extract increasingly detailed information about temperatures, pressures, fluid compositions, and deformation histories from minerals that experience the mountain-building events accompanying continental collision, or from sedimentary sequences that accumulated in the basins surrounding and within the supercontinent, recording changes in weathering patterns, erosion rates, and climatic conditions through variations in mineralogy, geochemistry, and sedimentary structures. The ongoing dispersal of Pangea's fragments continues today, with the Atlantic Ocean widening at rates of 1 to 2 centimeters per year, while the Pacific Ocean shrinks, Africa moving northward to gradually close the Mediterranean Sea, and India continuing to collide with Asia and drive the uplift of the Tibetan Plateau, processes that will eventually lead to a new configuration of continents, and perhaps hundreds of millions of years in the future, to the assembly of another supercontinent whose formation will again transform Earth's surface environments and create new challenges and opportunities for whatever forms of life persist through the transitions.